My dear students, Assalamu alaikum. Let's start lecture number 23 of CS 317 Operating Systems. This is the last lecture on the chapter of file management, for which we are using chapter 12 of the William Stallings book. In the last lecture, we discussed B trees, we explored file directories, we discussed file sharing, and we understood record blocking. Now we start our discussion on secondary storage management. Issues with storing files on secondary storage. On secondary storage, a file consists of a collection of blocks. The operating system or file management system is responsible for allocating blocks to files. This raises two management issues: allocation of disk space to files and keeping track of free space. These two tasks are related. That is, the approach taken for file allocation may influence the approach taken for free space management. There is an interaction between file structure and allocation policy. File allocation issues. Space is allocated to a file as one or more contiguous units referred to as portions. A portion is a contiguous set of blocks. The size of a portion can range from a single block to the entire file. The issues involved in file allocation are: when a new file is created, is the maximum space required for the file allocated at once? What size of portion should be used for file allocation? What sort of data structure or table is used to keep track of the portions assigned to a file? To keep track of allocated portions, DOS and some other systems use a file allocation table or FAT. Pre-allocation versus dynamic allocation. A pre-allocation policy requires that the maximum size of a file be declared at the time of the file creation request. In a number of cases, such as program compilations, the production of summary data files, or the transfer of a file from another system over a communication network, this value can be reliably estimated. However, for many applications, it is difficult, if not impossible, to estimate reliably the maximum size of the file. In those cases, users and application programmers tend to overestimate file size so as not to run out of space. This results in wastage of space on secondary storage. It is advantageous to use dynamic allocation, which allocates space to a file in portions as needed. Portion size. At one extreme, a portion large enough to hold the entire file is allocated. At the other extreme, space on the disk is allocated one block at a time. In choosing a portion size, there are 4 points to consider. Contiguity of space increases performance. So this will incline us to allocate a big portion to each file so that the file remains in one place and is fetched and processed quickly. Having a large number of small portions increases the size of tables needed to manage the allocation information. The smaller the portion, the greater the number of portions allocated to a file. If 5 portions are allocated to a file, the allocation table will have 5 entries for the same file. If you allocate a large portion to the file and it fits into this single portion, the allocation table will have a single entry for this file. This means that portion size is inversely proportional to file allocation table size. Having fixed sized portions, for example blocks, simplifies space reallocation. Suppose we allocate variable sized portions. A file takes up one portion of 3 kilobytes. When we delete this file, we have a free portion of 3 kilobytes. So the deletion of files leaves us with free portions of variable sizes. When we store a new file, we need to pick a portion that is large enough for the new file. So we have to search for a suitable portion in the available free portions. Suppose we allocate fixed sized portions. A file takes up 4 blocks. When we delete this file, we have 4 free blocks. These can be easily allocated to another file later. Having variable sized or small fixed sized portions minimizes waste of unused storage due to over allocation. If we allocate variable sized portions to files, we can allocate only as much as the file needs, and there will be no wastage of space inside the portion or internal fragmentation. If we allocate small fixed size portions to file, we can allocate only as many blocks as the file needs, and there will be wastage of space only inside the last portion. Alternatives for decision of portion size. Variable large contiguous portions. This provides better performance due to contiguity. The variable size avoids waste. The file allocation tables are small. Space is hard to reuse. Blocks. Small fixed portions provide greater flexibility in space reuse. They require large tables or complex structures for allocation. We do not strive for contiguity. Blocks are allocated as needed. Pre-allocation. In the case of variable large contiguous portions, a file is pre-allocated one contiguous group of blocks. This eliminates the need for a file allocation table. All that is required is a pointer to the first block and the number of blocks allocated. In the case of blocks, all of the portions required are allocated at one time. This means that the file allocation table for the file will remain of fixed size because the number of blocks allocated is fixed. Fragmentation of free space. Free space is fragmented when it is not contiguous. So if all files are in the start of the disk and all free space is at the end of it, free space is unfragmented. With variable sized portions, we need to find a free space large enough to accommodate our file. The following are possible strategies. First fit. Choose the first unused contiguous group of blocks of sufficient size from a free block list. Consider you want to store a file of 4 KB. Your free space list is this: 2 KB, 5 KB, 3 KB, 6 KB, 4.5 KB, and 7 KB. First fit provides you the second free space of 5 KB. The file will be allocated in the first 4 KB and 1 KB will be returned to the free space list. The free space list after allocation is 2, 1, 3, 6, 4.5 and 7 KB. Each successive allocation creates smaller free spaces which are more difficult to reallocate. Best fit. Choose the smallest unused group that is of sufficient size. Consider you want to store a file of 4 KB. Your free space list is this: 2, 5, 3, 6, 4.5 and 7 KB. Best fit provides you the second last free space of 4.5 KB. The file will be allocated 4 KB and 0.5 KB will be returned to the free space list. The free space list after allocation is 2 KB, 5 KB, 3 KB, 6 KB, 0.5 KB and 7 KB. Again, each successive allocation creates smaller free spaces which are more difficult to reallocate. Also, you have to scan the whole free space list. Nearest fit. Choose the unused group of sufficient size that is closest to the previous allocation for the file to increase locality. So you prefer a portion which is close to the previous portion that you allocated to the same file. Pause the video and find the answer to these questions. Task 1. Why do we dislike fragmented free space? Task 2. What is the cause of fragmentation of free space? File allocation methods. Three file allocation methods are in common use: contiguous, chained, and indexed. Contiguous allocation. With contiguous allocation, a single contiguous set of blocks is allocated to a file at the time of file creation. This is a pre-allocation strategy using variable sized portions, that is, a portion can have any number of blocks. The file allocation table needs just a single entry for each file, showing the starting block and the length of the file. Contiguous allocation is the best from the point of view of the individual sequential file. Multiple blocks can be read in at a time to improve I/O performance for sequential processing. It is easy to retrieve a single block if a file starts at block B and the ith block of the file is wanted. Its location on secondary storage is simply B plus I minus 1. Consequences of contiguous allocation. With pre-allocation, it is necessary to declare the size of the file at the time of creation. External fragmentation is the situation in which there are lots of small free spaces in storage. External fragmentation will occur, making it difficult to find contiguous blocks of space of sufficient length. From time to time, it will be necessary to perform a compaction algorithm to free up additional space on the disk. If you look at the new picture here, you will see that we have compacted our files. We have moved all the files to the start of the disk and we have defragmented the free space. Chained allocation. Allocation is on an individual block basis. Each block contains a pointer to the next block in the chain. The file allocation table needs just a single entry for each file, showing the starting block and the length of the file. Although pre-allocation is possible, it is more common to allocate blocks as required. Any free block can be added to a chain. There is no external fragmentation to worry about because only one block at a time is needed. To select an individual block of a file requires tracing through the chain to the desired block. Consequences of chained allocation. There is no accommodation of the principle of locality. The file is scattered and fragmented, as you can see from the picture. If it is necessary to bring in several blocks of a file at a time, a series of accesses to different parts of the disk are required. This affects performance more in a single user system, but may also be of concern on a shared system. In a single user system, mostly the processor is following locality, but the file is not allocated following locality. That is why performance degrades more in a single user system. In a shared system, because you are getting disk requests from many users, they are scattered, and even though you make a lot of file accesses, you have to make those accesses because you are accommodating a lot of users at the same time. To overcome this problem, some systems periodically consolidate files. In this new picture, you can see that we have consolidated the fragmented and scattered file B, and now all the chain is lying in one place. Indexed allocation. Indexed allocation addresses many of the problems of contiguous and chained allocation. Allocation may be on the basis of either fixed size blocks or variable sized portions. The file allocation table contains a separate one level index for each file. The index has one entry for each portion allocated to the file. Typically, the file indexes are not physically stored as part of the file allocation table. Rather, the file index for a file is kept in a separate block, and the entry for the file in the file allocation table points to that block. Consequences of indexed allocation. Allocation by blocks eliminates external fragmentation. Allocation by variable sized portions improves locality. In either case, file consolidation may be done from time to time. File consolidation reduces the size of the index in the case of variable sized portions. Indexed allocation supports both sequential and direct access to the file, and thus is the most popular form of file allocation. Please bear in mind that file consolidation will obviously take time. Free space management. Just as the space that is allocated to files must be managed, so the space that is not currently allocated to any file must be managed. To perform any of the file allocation techniques described earlier, it is necessary to know what blocks on the disk are available or free. We need a disk allocation table in addition to a file allocation table. Different ways of making such a table are bit tables, chained free portions, indexing, and free block list. Bit tables. This method uses a vector containing one bit for each block on the disk. Each entry of a 0 corresponds to a free block, and each 1 corresponds to a block in use. Look at the picture here. The bit vector is composed of 35 bits because there are 35 blocks. You can look at the bit vector and the picture and you will see that every free block is represented by a 0 and every allocated block is represented by 1. A bit table has the advantage that it is relatively easy to find one or a contiguous group of free blocks. You have to find a contiguous group of zeros. Thus, a bit table works well with any of the file allocation methods outlined. Another advantage is that it is as small as possible. However, it can still be sizable. Bit table size. The amount of memory in bytes required for a block bit map or a bit table is disk size in bytes divided by 8 into file system block size. For a 16 GB disk with 512 byte blocks, the bit table occupies 4 megabytes. If it can be kept in main memory, then the bit table can be searched without the need for disk access. The alternative is to put the bit table on disk. If each block is of 512 bytes or 0.5 KB, a 4 megabyte bit table requires 8,000 disk blocks. We can't afford to search that amount of disk space every time a block is needed. Even when the bit table is resident, that is, it is in main memory, an exhaustive search of the table can slow file system performance to an unacceptable degree. This is especially true when the disk is nearly full and there are few free blocks remaining. Accordingly, most file systems that use bit tables maintain auxiliary data structures that summarize the contents of subranges of the bit table. The table is divided logically into a number of equal size subranges. A summary table shows the number of free blocks and the largest free portion for each subrange. When the file system needs a portion, the summary table is scanned to find an appropriate subrange, which is then searched. Summarizing a bit table. For the picture that I have showed you earlier, the bit vector of 35 bits is this. Let us define a subrange to span 5 blocks. Look at this summary table. For each subrange, we identify the number of free blocks, the largest free portion size, and the bit vector. So if a file needs a portion of 3 blocks, it is useless to scan the first subrange. Chained free portions. The free portions may be chained together by using a pointer and a length value in each free portion. This method has negligible space overhead because there is no need for a disk allocation table, merely for a pointer to the beginning of the chain and the length of the first portion. This method is suited to all of the file allocation methods. If allocation is a block at a time, simply choose the free block at the head of the chain and adjust the first pointer or length value. If allocation is by variable length portion, a first fit algorithm may be used. The headers from the portions are fetched one at a time to determine the next suitable free portion in the chain. Again, pointer and length values are adjusted. Creating a chain of free portions. We keep a pointer to the first free portion and its length 0, which is the first free block, and 2, which is the length of the first portion, spanning blocks 0 and 1. Each first block of a portion contains its length. The chain of free portions is 0 length 2, 5 length 4, 14 length 4, 29 length 1, 32 length 3. If file C is deleted, we add its blocks to the chain. So you can see that the chain has altered. 0, 2, 5, 4, 14, 12, 29, 1, 32, 3. If further file E is deleted, we add its blocks to the chain. So the chain now becomes 0, 2, 5, 4, 14, 16, 32, 3. We need a portion of 5 blocks. We use first fit. Then we are going to allocate blocks 14, 15, 16, 17, 18. And the chain becomes 0, 2, 5, 4, 19, 11, 32, 3. Consequences of chained free portions. After some use, the disk will become quite fragmented and many portions will be a single block long. Every time you allocate a block, you need to read the block first to recover the pointer to the new first free block before writing data to this block. If many individual blocks need to be allocated at one time for a file operation, this greatly slows file creation. Deleting highly fragmented files is very time consuming. We have to add each portion of the file to the existing chain of free blocks. Indexing. The indexing approach treats free space as a file and uses an index table as described under indexed file allocation. For efficiency, the index should be on the basis of variable sized portions rather than blocks. Thus, there is one entry in the table for every free portion on the disk. This approach provides efficient support for all of the file allocation methods. Free block list. In this method, each block is assigned a number sequentially and the list of the numbers of all free blocks is maintained in a reserved portion of the disk. Depending on the size of the disk, either 24 or 32 bits will be needed to store a single block number. The size of the free block list is 24 or 32 times the size of the corresponding bit table and thus must be stored on disk rather than in main memory. Let us talk about the size of the free block list. A 2 terabyte disk has blocks of 512 bytes. Total number of blocks is 2 terabytes divided by 0.5 kilobyte, and this gives us 2 raised to the power 32 blocks. Each block must be represented by a 32-bit or a 4-byte number. The space penalty is 4 bytes for every 512 byte block. Total size of free block list is 4 bytes into 2 raised to the power 32, which is 16 gigabytes. The free block list takes up less than 1% of the total disk space, so it is worth it. Optimizing the free block list. Although the free block list is too large to store in main memory, there are two effective techniques for storing a small part of the list in main memory. The list can be treated as a push-down stack, with the first few thousand elements of the stack kept in main memory. When a new block is needed for allocation, it is popped from the top of the stack, which is in main memory. When a block is deallocated from a file, it is pushed onto the stack. A transfer between disk and main memory happens only when the in-memory portion of the stack becomes either empty, no free blocks, or full. The in-memory stack cannot receive more blocks. This technique gives almost zero time access mostly. The second way of doing things is the list can be treated as a FIFO queue with a few thousand entries from both the head and the tail of the queue in main memory. A block is allocated by taking the first entry from the head of the queue and deallocated by adding it to the end of the tail of the queue. A transfer between disk and main memory happens only when either the in-memory portion of the head of the queue becomes empty, no free blocks, or the in-memory portion of the tail of the queue becomes full, the in-memory tail cannot receive more blocks. Now we talk about something known as a volume, a collection of addressable sectors in secondary memory that an OS or application can use for data storage is a volume. The sectors in a volume need not be consecutive on a physical storage device. Instead, they need only appear that way to the operating system or application. A volume may be the result of assembling and merging smaller volumes. Continuing, the term volume is used somewhat differently by different operating systems and file management systems, but in essence, a volume is a logical disk. In the simplest case, a single disk equals one volume. Frequently, a disk is divided into partitions, with each partition functioning as a separate volume. It is also common to treat multiple disks as a single volume or partitions on multiple disks as a single volume. Now we talk about a file allocation gone wrong. Consider the following scenario. User A requests more space to add to an existing file. The request is granted and the disk and file allocation tables are updated in main memory but not yet on disk. The system crashes and subsequently restarts. User B requests more space and is allocated space on disk that overlaps the last allocation to user A. In simpler words, the free blocks that were allocated to A have now also been allocated to B. User A accesses the overlapped portion via a reference that is stored inside A's file. User A is inadvertently accessing user B's file and vice versa. This difficulty arose because the system maintained a copy of the disk and file allocation tables in main memory for efficiency. Solution to the problem. To prevent the type of error we just saw, we take the following steps. Lock the disk allocation table on disk. This prevents another user from altering the table until this allocation is complete. Search the disk allocation table for available space in the resident copy of the disk allocation table. Resident copy means the copy in the main memory. Or read the table into main memory first and then search. Allocate space, update the disk allocation table, update the disk. Updating the disk involves writing the disk allocation table back onto disk. For chained disk allocation, it also involves updating pointers. Update the file allocation table and update the disk. Unlock the disk allocation table. This technique will prevent errors and increase reliability of our allocation and our free space management. Reliable batch allocation. When small portions are allocated frequently, performance suffers. A batch storage allocation scheme involves obtaining a batch of free portions from the disk for allocation. The corresponding portions on disk are marked in use. Allocation using this batch proceeds in main memory. When the batch is exhausted, the disk allocation table is updated on disk and a new batch is acquired. If a system crash occurs, portion on the disk marked in use must be cleaned up in some fashion before they can be reallocated. The technique for cleanup will depend on the file system's characteristics. The last part of this chapter is file system security. Control of users' accesses. Through the login name and password, a user is identified to the system. Each user has a profile specifying permissible operations and file accesses. The operating system can enforce rules based on the user profile. The database management system, however, must control accesses to specific records or even portions of records. For example, it may be permissible for anyone in administration to obtain a list of company personnel, but only selected individuals may have access to salary information. The issue is more than just a matter of level of detail. Whereas the operating system grants a user permission to access a file or use an application, following which there are no further security checks. The database management system must make a decision on each individual access. The DBMS's decision will depend not only on the user's identity but also on the specific parts of the data being accessed. Access matrix. A general model of access control is an access matrix. The basic elements of the model are as follows. Subject. An entity capable of accessing objects. Generally, the subject is a process. Object. Anything to which access is controlled. Examples include files, portions of files, programs, segments of memory, and software objects like Java objects. Access right. The way in which an object is accessed by a subject. Examples are read, write, execute, and functions in software objects. Dimensions of the access matrix. One dimension of the access matrix consists of identified subjects. Typically, this list will contain individual users or user groups, although access could be controlled for terminals, hosts, or applications instead of or in addition to users. The other dimension lists the objects. At the greatest level of detail, objects may be individual data fields, more aggregate groupings such as records, files, or even the entire database may also be objects in the matrix. Each entry in the matrix indicates the access rights of that subject for that object. In practice, an access matrix is usually sparse. In the access matrix that you see over here, the rows represent subjects or users and the columns represent objects or files. The last two columns are for accounts and we are not going to talk about them. We are going to focus our discussion on the files. Access control list. The matrix may be decomposed by columns, yielding access control lists. Thus, for each object, an access control list lists users and their permitted access rights. The access control list may contain a default or public entry. This allows users that are not explicitly listed as having special rights to have a default set of rights. Elements of the list may include individual users as well as groups of users. Capability tickets. Decomposition of access matrix by rows yields capability tickets. A capability ticket shows authorized objects and operations for a user. Each user has a number of tickets and may be authorized to loan or give them to others. Because tickets may be dispersed around the system, they present a greater security problem than access control lists. The ticket must be unforgeable. One way to accomplish this is to have the operating system hold all tickets on behalf of the users. These tickets would have to be held in a region of memory inaccessible to users. So what did we learn? We explored secondary storage management. We had a detailed discussion on file allocation methods. We talked about free space management. We understood the challenges of file system security. Things to do: read the book, find the answers to the tasks that I have set you and submit them via Google Classroom. Note your questions for the online session and email your suggestions to me. Take care. Allah Hafiz.